All right, PCH. So already this week we've talked about graphing sine and cosine. We've talked about modeling real-world situations with those two functions. And so now what we're going to talk about is the graphing the reciprocal functions of sine and cosine, which are cosecant and secant. And so I'll give you a second to read this paragraph here. All right, so basically what this paragraph is saying is that, hey, like sine and cosecant are reciprocal functions. We know how to graph sine, and so let's see if we can plot some points in this table here for cosecant and then graph it and see what the graph looks like. Okay, we'll start with 0. Again, if we're trying to find the cosecant of this value, we need to take 1 over sine. 1 over sine, which is 0, that's going to be undefined. So already off to a great start here trying to graph this reciprocal cosecant. All right, 0.7, we can think about that as like 7 over 10. Let's see, when I graph 10 divided by 7, get about 1.43. Reciprocal of 1 is just 1. Again, this will be 1.43. Sorry to bore you as I fill out this chart. But again, all I'm doing here is taking the reciprocal of my sine of x to get cosecant of x at each of these x values. Okay. One thing that I notice when I'm looking at this table that I've just come up with for cosecant of x, just like sine of x, we have a bunch of values that are repeating. 1.43, even have 1 repeating a few times, undefined repeating a few times. So just like sine, I can kind of predict that, you know what, I think there's going to be some sort of pattern when it comes to graphing cosecant. And let's see if that's right. Okay, so at 0, we're undefined. I'm just going to leave that one blank for now. So I'm going to go ahead to pi over 4. 1.43, that'll be somewhere up here. Of course, OneNote's not cooperating. Ooh, another thing I noticed here, that in my sine and cosecant graphs, both of my graphs have the point pi over 2, comma 1. So they share these points in common. Interesting. All right, 3 pi over 4, 1.43. At pi, we're undefined, so there's like nothing there again. 5 pi over 4, we're negative. Again, we see that the points share, or the two functions share the same point here. Negative 1.43 again. Oh my gosh, OneNote is so frustrating. I apologize. And then of course 2 pi is undefined. So what do we see? Like this is really weird. First, let's kind of think about what do we picture on a graph when we have something that's undefined. Remember, we were talking about domain restrictions way back in try 1. Whenever we had a domain restriction, what did that show up on the graph as? That's right. And whenever we had something that was undefined, that showed up on the graph as a vertical asymptote. And so I'm going to go ahead and fill in my vertical asymptotes here. All the points where cosecant of x is undefined. Cool. I'm going to ask you in just a second to tell me, what do we notice about all the spots where we have vertical asymptotes compared to what points are on the sine of x graph? Right, but from here I'm just going to continue connecting the dots. Ooh, so it looks like we have some sort of parabola looking graph. And again, what do we notice about these parabolas as far as how they compare to our sine of x graph? I'll give you a second to think, and I'll have you answer those questions. Okay, you've had some time to think, you've had some time to respond. I'm really excited to read your answers. I'm curious what kinds of patterns you notice. One thing that I notice is that anytime I have a point that lies on my x-axis for my sine of x graph, so we see that point here at 0, pi, and 2 pi, it's going to show up as a vertical asymptote on my cosecant graph. And it looks like if I were to continue graphing this, that would continue to be the case. I can expect to have a vertical asymptote here at this point, here at this point as well. So that's something to keep in mind. Another thing I really hope you realized is that our graph of cosecant, the only points that it shares in common with my sine of x graph are these points here that are maxes and mins on my sine of x graph. Whenever I have a max on my sine of x graph, I can see that in my cosecant graph, I'm going to have a parabola with a vertex that shares that same point and is pointing away from the midline of my sine of x graph. Right? It's pointing away from my graph. And I notice the same thing here when I have a minimum on my sine of x graph. If I have a minimum, again, I'm going to have some sort of upside down parabola that shares a vertex with the point of that minimum on my sine of x graph. Okay, just so we can see this more clearly, I want to show us a cool little graph here that shows as we're graphing sine of x, what does it look like for cosecant of x? And you'll see that yes, if we were to continue this pattern past 2 pi, you would continue to see these same things that we've been talking about. Now my question for you now is, we know that cosine and secant are also reciprocal functions. So I want you to take a guess as to what those graphs might look like. We know what cosecant of x looks like. How might secant of x compare to our cosine of x graph? This shouldn't have been too tricky because we know that our cosine of x is the same function as our sine of x function, except it's been shifted horizontally a little bit, right? Both sine of x and cosine of x are sinusoidal functions. We see cosine also has maxes and mins, and so hopefully you were able to predict that, you know what, I think that the secant of x graph is also going to have these weird parabola looking things that share a point with the maxes and mins on my cosecant of x graph. And we can see that here with this little animation. Again, it looks just like our sine of x and cosecant of x graphs, but slightly shifted. And so if we think about trying to graph cosecant of x and secant of x, all we really have to do is graph our sine and cosine of x functions, which we're really good at already. We've been practicing that. And then we can come up with our cosecant and our secant graphs really, really easily. And that statement I just made is summed up pretty nicely down here. Again, all we have to do to graph these reciprocal functions is graph sine and cosine first. And then graphing the reciprocals is going to be a breeze. Now what happens when our graphs have some sort of transformation? Like what if we have a cosecant graph that's been shifted to the left pi? Like, is that going to complicate things for us? What do you think? I want you to try constructing a set of rules for how we might graph a transformed cosecant graph from the graph of sine of x. Okay, so when we were graphing just y equals sine of x, y equals cosecant of x, really all we needed to do and what we were able to do was say, okay, if I want to graph y equals cosecant of x, I can just graph y equals sine of x and then do my little special magic trick where I draw my parabolas. I wonder if that works with transformations. If I have the graph y equals 2 times the cosecant of 2 times x plus pi, which is what you see graphed here, am I able to do what I did earlier and just switch out this cosecant with sine? I want you to predict for me, if I graph this top function, this y equals 2 times the sine of the same transformations that you see in this graph here, what do you think we're going to see? All right, yeah, I'm really hoping, most of us said, yeah, I think we're still going to see our sine graph have a maximum at this point of negative 3 pi over 4. And I think it's going to have a minimum at an x value of negative pi over 4. Let's see if that happens. That's exactly what happens. Again, that's such a cool thing about these reciprocal functions. It doesn't matter what transformations you're doing. It doesn't matter, like you could have the craziest graph ever of cosecant or function, and all you have to do is replace it with sine of x, graph that sine of x function, and then do your parabolas. Draw your vertical asymptotes. And the same thing works with cosine and secant. And so what I want us to do is a little bit of practice here. All right, go ahead and pause the video. I want you to take a second, just copy down these axes here. We've been doing this all week, so I don't want to spend time drawing our axes right now. I really want to focus on the graph. Okay, so if we're trying to draw our graph y equals 2 times secant of half x minus 3, I know that I'm going to start with 2 times cosine of 1/2 x minus 3 and go from there. Okay, so my cosine function, it's been moved down 3, so at negative 3 here, that's where I'm going to have my midline. Again, my period, because of this coefficient out front of my x is 1/2, my period is now 4 pi, and that's what you see for my x-axis here. My amplitude is 2, so my range for my cosine function is going to be from negative 5 to negative 1. And we're ready to graph. Okay, cosine I know starts here, again, because our amplitude's 2, we'll be at our midline at pi, minimum at 2 pi, midline at 3 pi, maximum here at 4 pi. Okay, cool. So what do we know? What do we remember about secant? My first thing is, okay, any point on the midline, that's going to be a vertical asymptote. So I'm going to draw that in. That should be at 3 pi. I did not draw a straight line. I apologize. Another vertical asymptote here at pi. What's the only other thing I have to do? At each of my maxes and mins on my cosine graph, I just have to draw a parabola. Of course, one that's pointing away from the midline, away from my cosine of x graph. In PCH, that is the graph of y equals 2 times secant of 1/2 x minus 3. The last thing I want to have us think about before we get to class on Monday is if we had to narrow this down to 3 short steps. What is the process for graphing cosecant or secant? Think about where we start, and I've said it a few times in this video. How do we find our asymptotes? How do we find the vertexes for our parabolas? How do we know which way or which direction our parabolas are facing? Again, just as it says here, be specific. And this is where we will start on Monday. Have a great weekend, y'all.